Have you ever thought about light as something more than what just lets you see? What if you thought of it as a fundamental force of nature that you can control? Today, we're not just going to study physics, we are going to assemble a toolkit that will let us master light, to bend it, to bounce it, and to shape it to reveal the secrets of the universe, from the teeny tiny to the impossibly far away.
So, really, what if you could? What if you had the power to take a ray of light and just tell it exactly where to go? It sounds like something out of a sci-fi movie, right? But it's the reality of ray optics. And you're about to understand the fundamental tools that make everything, from your phone camera to those giant telescopes, possible.
Okay, so here's the game plan. We're going to start with the two absolute unbreakable rules of light. Then we'll see how curved mirrors use one of those rules to make images. After that, we'll switch gears to lenses and the second rule. We'll even uncover a special power-up for trapping light. And finally, we'll put all our new tools together to build instruments that let us see way beyond our own eyes.
It all starts right here. You know, every complex optical instrument in the entire world is built on just two simple, elegant ideas about what happens when light hits something. Does it bounce or does it bend? That's it.
So the first tool in our kit is reflection. Just think of it like a perfect, predictable bounce of a billiard ball. The angle that a ray of light hits a mirror, we call that the angle of incidence, is exactly the same angle that it bounces off. Simple. The second tool is refraction. This is what happens when light goes from one thing into another, say from air into a glass of water. It actually changes speed, and that causes it to bend. How much it bends all depends on something called the refractive index.
So, we know light bounces predictably off a flat surface. But what happens if we change the shape of that surface? Let's take that super simple rule of reflection and apply it to a curved mirror, because that's where we can start focusing light to actually create an image.
You might think you'd have to track every single ray of light, but nope. Predicting what a mirror will do is surprisingly easy. By just tracing a couple of key rays, like one that comes in straight and then bounces through a special spot called the focal point, we can see exactly where they cross. And that point of intersection? That's where our image shows up. It's an awesome visual shortcut.
But what if we need more than just a sketch? What if we need to be mathematically certain? Well, that's where this beautiful little formula comes in, the mirror equation. It connects the object's distance, which is u, the image's distance, v, and the mirror's focal length, f. It's basically the blueprint that perfectly describes that geometry, letting us calculate the exact location of an image without drawing a single line.
Now, this is super important. Not all images are created equal. If the light rays physically come together and meet at a point, we get a real image, the kind you can actually project onto a screen. But if the rays only look like they're coming from a point behind the mirror, we get what's called a virtual image. You know, like the one you see of yourself in the bathroom mirror every morning.
All right, we've totally mastered bouncing light around with mirrors. Now it's time for our second major tool, refraction. Instead of bouncing light, we're going to pass it through some carefully shaped glass to bend it exactly where we want it to go. This is the world of lenses.
And just like with mirrors, we've got some simple rules to follow. A ray of light that comes in straight and parallel is always bent to pass through the focal point. And a ray that goes right through the dead center of the lens, it just keeps on going, totally straight. And where those two rays cross paths, you got it, that's your image. Simple, predictable, and incredibly powerful.
And yep, you guessed it, there's an equation for this too, the thin lens formula. It looks almost identical to the mirror equation, but with one tiny, crucial difference. See that minus sign? That little sign change is all we need to handle the math for lenses. This formula is our master key, letting us calculate precisely where a lens will form an image, whether it's in a magnifying glass or a super high-powered camera.
Now for something really cool, a truly fascinating phenomenon. We know that when light goes from a dense material, like water, into a less dense one, like air, it bends. But what if we keep increasing the angle? Something pretty amazing happens. We unlock a whole new ability, the power to trap light completely.
The key to this power is something called the critical angle. Think of it as a tipping point. If light hits the surface at any angle less than this, some of it will escape. But once you hit that exact critical angle, or go beyond it, refraction just stops. The light literally can't get out. 100% of it is reflected right back into the material.
This is the secret to why diamonds sparkle so brilliantly. The critical angle for a diamond is an astonishingly small 24.41 degrees. This means that almost any light that enters a diamond gets trapped. bouncing around inside from facet to facet, unable to escape until it hits a surface at just the right angle to exit. That's not just sparkle, that's a light cage in action.
But this isn't just a pretty effect for jewelry. Total internal reflection is the engine of our modern connected world. Inside an optical fiber, light signals bounce millions of times off the inner walls, always at an angle greater than the critical angle. This lets data travel for miles and miles with almost zero loss of signal. It's literally the backbone of the internet.
Okay, so our toolkit is assembled. We have reflection from mirrors, we have refraction from lenses, and we've got the superpower of total internal reflection. It's time to open up that toolkit and start building. Let's see how these simple principles combine to create instruments that completely extend the power of human sight. So first up, let's look at the microscopic world. A compound microscope is a classic two-step process. The first lens, the one down near the slide, is the objective. It creates a magnified real image of a tiny object. Then, the second lens, the eyepiece you look through, acts like a simple magnifying glass to blow that first image up even further. It's a brilliant one-two punch using our lens tools.
Now, let's look in the other direction, out into the cosmos. For giant telescopes, trying to make a huge, perfect lens is incredibly difficult and crazy expensive. So astronomers had a better idea. They swapped tools. A reflecting telescope uses a massive curved mirror as its objective. Why? Well, mirrors can be made much, much larger. They gather more of that faint light from distant galaxies, and they don't have the color fringing problems that can plague big lenses.
So there we have it. We went from two simple rules, bouncing and bending, to building instruments that can visualize a single cell or a galaxy millions of light years away. We have literally built new ways of seeing the world. And this very toolkit is still inventing the future as we speak. From quantum computing to new kinds of medical imaging, the fundamental act of bending light to our will is really just getting started. The only question is, what will we choose to see next?